We will start now with a new chapter, which is two-dimensional steady-state conduction. So until now, we worked with 1D cases. Of course, solution in 1D is much more straightforward. Whenever we go to 2D and 3D, things will be much more complex, and we need to develop sometimes the equation analytical solution is really challenging, so we can go to numerical techniques. So in this chapter, we'll introduce how we can use numerical techniques to solve 2D problems. So you know that we might encounter problems where conduction occurs in more than one dimension. In this chapter, we'll focus on 2D steady-state conduction, and we'll develop some numerical methods that will help us into accurately predicting temperatures and heat rates. So for example, let us consider a long prismatic solid in which there is a 2D heat conduction. You have two surfaces that are insulated, and the others are at different temperatures, T1 and T2. So heat transfer by conduction from surface 1 to surface 2. So according to Fourier's law, the local heat flux in the solid is a vector that is everywhere perpendicular to the lines of constant temperature. So always heat flux is perpendicular to line at constant temperature. But if these lines are not parallel, we don't have 1D, we'll have 2D, as you can see in this figure. So you are imposing two adiabatic conditions at two surfaces. So here you have insulation, okay? And here you have different temperature between this surface is at T1 and this surface is at T2, okay? And here, because you don't have the same area and not same shape, so if you follow the heat flux line, so the heat flux will have two dimensions here, and it will be perpendicular, okay, to the line of constant temperatures. The line of constant temperatures here will be curves, okay, which will justify having temperature variation in two dimensions. And of course, this is much more complex than a wall of constant area. So that's why a solution of temperature distribution in this domain is more complex and can be done using analytical method or numerical method. Now, in any conduction problem, we need to find the temperature distribution. If we go back to the general equation and we simplify it, okay, no generation, so Q dot is 0. Steady state, so derivative of temperature with respect to time is 0. So, but for conduction term, instead of just having variation in X, we'll have also variation in Y. So the differential equation to solve for such problem will be more complex. Okay, will not go back. There is of course analytical techniques to solve these equations, but we'll not go back to analytical cases for 2D problems. We'll develop some numerical methods that will help us to solve such equations. So methods for solving the heat equation include use analytical or also numerical approach. Analytical method involve effecting an exact mathematical solution to the heat equation. However, in such cases, it is more difficult as we'll be dealing with partial differential equations. Unlike the analytical approach, numerical techniques may be used to obtain accurate results for complex 2D or 3D geometries, including involving a wide variety of boundary conditions. Now, I think that you have taken already some numerical techniques, okay? So for example, we can use the finite difference equations. What is the idea here? It consists of dividing our domain into small elements, okay? And each element will be constituted by a center and faces. So if I take, let's say, a certain rectangular shape, I need I consider delta X, delta Y, and I have these four faces. And I can write the energy balance for each of my cells, okay? By writing the energy balance and solving for it, using also appropriate boundary conditions. Yani for example, at the surface here, if I have imposed temperature, I can say the temperature at this face is known, and I use it as a boundary to solve for the temperature at this node, then at this node, etc. Okay. So numerical solution will allow finding the temperature at discrete points, depending on how the domain is divided into delta x and delta y discretization steps. Therefore, the first step is to divide the medium into a number of small regions and assigning to each a reference point that is at its center. So for each element, I have to define the node, the center, and the four faces if you want limiting it. Now, of course, in general, larger the number of elements, the more accurate the solution is. Because here you will solve for temperatures at points. It's not continuous like in the case of analytical solutions. In analytical solutions, you find t function of x and y. So for any x and y, you can find temperature t. However, in numerical techniques, you solve at some points. That's why increasing the number of points will increase the accuracy of your solution. Now, so the center point is called a nodal point or simply a node, and all the nodes form a nodal network, grid, or mesh. The x and y location are considered by m and n indices, and then we can vary m and n in order to cover the whole domain. Now, each node will represent a certain region, and its temperature is a measure of the average temperature of the region. And we consider that if I know the temperature here, it is the average temperature of this cell. Okay. And the numerical accuracy of calculation will, of course, depend strongly on the number of nodes, because large numbers will make a finer mesh and will give accurate results. Now, what are the equations that we will write for each cell? It's simply the energy balance. So to find the temperature distribution numerically, a conservation equation must be written for each of the nodal points. Therefore, we end up with a set of equations that are solved simultaneously for the temperature at each node. Applying a nodal network to a 2D system with no heat generation and uniform thermal conductivity, it's necessary to work with an approximate or finite difference form of the heat equation. So here, this is your heat equation. This heat equation is in differential form. How to transform it to numerical form? You need to, for example, let us start by the first derivative. If I tell you del t by del x, how you can transform it to a numerical form? You put it as delta t over delta x. And here you have several approaches how to define delta t over delta x. I will discuss this together. For example, you are interested by del t by del x at this point, at node I. Okay, but you have a node before it, I minus 1, let's say. And you have a node after it, I plus 1. There is several ways to define derivative of delta t with delta x. And for example, you can say I will consider these 2 points. And I do ti minus 1 over delta x, this distance. Or I can use these 2 points. And I say delta t over delta x can be written as ti plus 1 minus ti over this distance. What we call the centered scheme will take the two extreme points, yani ti plus 1 minus ti minus 1 over 2 times delta x. Okay, if we consider uniform grid, yani delta x to be the same everywhere. So what formula to decide on depends on the physics of the problem. Okay, so if you take after CFD, you will learn, for example, in case I have convection, the upwind scheme is better. In case I have conduction, I can take the centered scheme, etc. Okay, so depending on the physics of the problem, one method will be more, if you want, accurate than the other. So here, we want to define, as we said, a numerical form for the second derivative. So how to calculate the second derivative at a certain node, mn? So this notation mn is will show you the following. M represent, okay, different nodes in the same. And here, if this is m, okay, m minus 1 is the one just in the same row just before it, and m plus 1 in the same row just after it. Okay, so if you have the same index m, this means that you are in the same column. And if you have the same index n, this means that your nodes are in the same row. So m stands for the number of column you are in, and n stands for the number of row your cell is in. Okay, so now if I want to evaluate the second derivative of t with respect to x, I can say that it's equal to the first derivative at m plus half n. يعني, if you want, if I take, this is my cell, okay, and this is my node. mn represent, as we said, the number of column and the number of row. I consider that this is my face. This face, okay, is we call it m minus half. Yani it's just between two nodes, while this node here is at m minus 1. And the node just after is m plus 1. While for my face, if I take the face here just after, it's m plus half. Okay, so I can define now the second derivative as the first derivative at this face minus the first derivative at this face over the distance between the two faces over delta x. Okay, and I can do the same in y direction, but now in y direction I vary the index n. Okay, so I say del t by del y mn plus half minus del t by del y mn minus half over delta y. Okay, and also now I need to replace del t by del x. So when I consider this face, when I consider del t by del x at face m plus half here, okay, I can consider the point just after the face and just before the face. So it's tm plus 1n minus tmn over the distance between the two. For a uniform grid, the length of the side will be equal to the distance between the centers, so over delta x. And if I replace now del t by del x at this face, I will use tmn minus tm minus 1n over this distance, which is delta x. If you replace now these by their expressions, okay, you end up with the following relation. Okay, you end up with the following relation for the second derivative of t with respect to x. It can be approximated as tm plus 1n plus tm minus 1n minus 2tmn over delta x squared. And the same for the second derivative with respect to y. But as we said, now we vary the index of the row. So tmn plus 1 plus tmn minus 1 minus 2tmn over delta y squared. And if we consider a uniform grid with delta x equal to delta y, okay, then this will simplify things a lot, because if you replace in your equation, what was your differential equation? Second derivative of t with respect to x plus second derivative of t with respect to y equals to 0. Okay, So if you replace by the numerical form, and you say, if I consider delta x equal delta y, you can take delta x square or 1 over delta x square in factor. Then you end up with tm plus 1n plus tm minus 1n minus 2tmn plus tmn plus 1 plus tmn minus 1 minus 2tmn again equal to over delta x square equals to 0. So because delta x equal delta y, you can say we can take same denominator, and since it's equal to 0, you can simplify delta x square, and this will be your equation. Okay, for each cell you can write the differential equation. Okay, and you end up with a set of equation with a certain number of unknowns, and of course you need to use boundary conditions to solve your problem. Yani, let's say, for example, this is a simple domain, a square domain. Let us consider that that the temperature at this surface is given. Okay, so you can use this temperature to solve for your temperature at all different nodes. Okay, we'll take examples of this to see how we can apply these techniques using the appropriate boundary conditions. So if we have each node will have an equation. Okay, so if you divide your system, let's say, into a certain number of columns and a certain number of rows. Okay, for example, if you say I will consider 2 columns, 3 rows. So you have 2 times 3 nodes. So for each node, you need to write the corresponding equation. Okay, so hence for the mn nodes, the heat equation, which is an exact differential equation, is reduced to an approximate algebraic equation. This approximate finite difference form of the heat equation may be applied to any interior node that is equidistant from its 4 neighboring nodes. It requires simply that the temperature of an interior node be equal to the average of the temperature of the 4 neighboring nodes. Okay, now how we will apply energy balances and how we can solve for such systems. So in this method, the finite difference equation for a node is obtained by applying conservation of energy to a control volume about the nodal region. The energy balance is formulated by assuming that all the heat flow is into the node. For steady state conditions with generation, the energy balance will be En plus E generation equals 0. Now you can tell me why we need to assume this. Maybe we have E out. It's right. But if you do the assumption that all fluxes are coming in, okay, this is an assumption. If you replace it numerically and you get a negative result, this means that E is not in, it's out. Okay, so you have the right to do the assumption that all of your heat flows are towards the node. If you get a positive result, your assumption is right. If you get a negative result, then the heat flow will be in the opposite direction. Okay, and since we are working in steady state conditions, the general equation will be En plus E generated equal to 0. And in case you have no generation, then the equation will be summation of En is 0. Okay, and here, of course, you should have something out. So any flux that is coming in should have on the opposite side a flux that is getting out in order to do the balance. Yani here, when you do sum of En 0, you have some of these will be positive and some of these will be negative in order to cancel out. Okay. Let us see it in a certain example. Okay, let us consider an element at the center of surrounded by 4 neighbors. It's not at the extremity. You will see that what we will do with cells at extremity after. So now consider that you have a central cell surrounded by 4 cells, and you want to write the energy balance for this cell. Okay, so we said that we'll consider possibility of generation and conduction. So here it's a solid. Heat can be transferred only through solid by conduction, and we have steady state case with possible generation. So as we said, the equation will be reduced to summation of En plus E generation equal to 0. And we assume that all conduction flux are towards the center. And as I told you, if you got a positive result, this means that the flux will enter the cell. If you get a negative result, this means that the flux will exit the cell. Okay? So now, if you want to write the expression of conduction through the phases, okay, we have conduction through the different phases. And we know the expression of Q conduction. Q conduction is minus K. If I consider an X direction, okay, it's minus K dt by dx. Please pay attention. It's minus K dt by dx if you take X like this, okay, and you consider the flux in positive X. But what if you consider on the following cell, you are taking the arrow to be opposite. So if you are taking the arrow to be opposite, then the value, the numerical value of this flux will be plus K dt by dx. So pay attention for this, okay? And to compute dt by dx here, for example, you can say that at this phase, it's Tmn minus Tm minus 1n over this distance, which is delta x, okay? While for this phase here, what is dt by dx? It's the temperature at this node, which is m plus 1n, minus Tmn over this distance, which is delta x, okay? Now, what about if you have volumetric generation in this cell? If you have volumetric generation, if you work in 2D, you can consider that the depth is 1, okay? So what will be the generation heat? It will be Q dot times volume. What is your volume here? It's delta X times delta Y times 1, okay? So what will be the general equation? Sum of conduction fluxes from the different phases plus generated rate equals to 0. And now, as we said together, okay, we will compute these fluxes for the different phases, okay? So you can say, when I assume that the flux is entering the cell, the temperature of this node should be larger than the temperature of this node. So how I can write, if you want, delta T over L, it's the temperature at this point, Tm minus 1n, minus the temperature at this point, Tmn over delta X. And if you try to do minus Ka dt by dx, you'll get exactly the same result. Okay, why? Because the area here, what is the area? The area is delta y times the depth. So delta y times 1. And what is dt by dx? If we want to write it in numerical form, this is x direction. So I take t at this point minus t at this point over this distance. Okay, so this can be replaced by Tmn minus Tm minus 1n over delta x. And if you enter the minus here, you get here it's a plus minus Tmn plus Tm minus 1n as we got here. Okay, so you have to approach, or you use the formula here, or you say, since I assumed the flux in this direction, then to be positive, this temperature should be larger than this one. So I do temperature here minus temperature here. Okay, while if you take this face, the expression will be plus Ka dt by dx, because now your flux is opposing x positive direction. So it's plus Ka dt by dx, and you can replace dt by dx by temperature at this node, Tm plus 1n, minus Tmn over delta x. Or in a second way of thinking, you can say, if I put the flux in this direction to be positive, the temperature at this node should be larger than this one. So I take Tm plus 1n minus Tmn over delta x. I will do the same in y direction. To compute this flux, I assumed it's positive in this direction. So to be positive in this direction, the temperature at this node is larger than this one. So I do Tmn plus 1 minus Tmn over delta y. And what about the area here? The area is delta x times the depth, which is 1. So this flux is K delta x1 times Tmn plus 1 minus Tmn over delta y. Finally, for this heat flux, to be positive in this direction, this temperature should be larger than this one. So I do Tmn minus 1 minus Tmn over delta y. So these are the expression of my 4 conduction fluxes. I can substitute them in the equation. If you substitute in the equation, okay, and you consider that delta x is equal to delta y, you can simplify to get the following relation. Okay, which is Tmn plus 1 plus Tmn minus 1 plus Tm plus 1n plus Tm minus 1n plus Q delta x square over K minus 4Tmn equals to 0. So all we did is to replace these in the formula. But if you have delta x equal delta y, this will simplify things, because look, delta y over delta x will cancel out. Okay? And you can take K into factor. So if you add these 4 terms, okay, you get, first look, Tmn is present everywhere. So you get minus 4 Tmn plus Tm minus 1n plus Tm plus 1n plus Tmn plus 1 plus Tmn minus 1 times K, of course. So this is why here I divided by K all terms. If you divide by K all terms, you will get here your generation over K. Your generation was Q delta x delta y. But since we consider delta x equal delta y, so it's Q delta x squared. And since we divided by K all terms, so you will end up with plus Q delta x squared over K. So this is the equation for each cell. Each of your cells that is surrounded by 4 other cells will be of this form. Okay? And you need to write for each cell such equation, so you end up with a linear system. With a linear system, let's say of n of a certain number of equation with a certain number of unknown that you can solve. Now, what about what is challenging here is not cells at center, it's cells at extreme points, at extreme surfaces. And we'll discuss this together next time. What to do with a cell that is exposed to the surrounding. Here we should use appropriately the boundary conditions, okay? Because whenever you have a cell having a node at the free surface, you need to use boundary condition appropriately in order to write the equation for yourself. Okay, so we will tackle this idea next time. Any question on this before we stop?
No.
Okay.
No, doctor.
Bye.